All right, now that we're done with two-dimensional vectors, let's take a look at three-dimensional vectors. And in 3 dimensions, we're going to use the Cartesian method almost exclusively. And so x, y, and z, typically in this book, we'll call xy plane will be the horizontal, like on the floor, and z will be up. So we'll define, just like we defined I hat and j hat, we'll define k hat in the z direction. And this is a right-handed system. And when we talk about cross product, we'll show more what that means. Now, if we have a vector A and we put its tail at the origin, then we can project its x, y, and z parts. And you'll notice that the way to do that is you drop straight down to the xy axis, then you call this A prime, and then you'll break that up into its x and y parts. So if I think of the blue triangle, then A prime squared plus A z squared will give me A squared. And then if I think of the gray triangle, A prime squared will be ax squared plus ay squared. I'm going to plug that in for A prime, and we get the three-dimensional Pythagorean. Still just the square root of the sum of the squares of the components. We'll be using that a lot. Now, if we then take our magnitude and divide it into our vector, and since it's a scalar, we just do a component by component, then we'll have what we call the unit vector in the direction of A. We've divided out the magnitude and the length, and therefore it's just magnitude 1, hence unit. And so in some ways it's pure direction. And we can write the vector as A times our unit vector. Now notice if we draw that up and we take the angle between the vector and say AX or AY or AZ, then that gives me 3 angles. We're going to call those the direction angles, and their cosines are going to be AY, AX over A. If you have to sort of visualize, it's easier to visualize it in the Z. You see you got your A and your AZ and your A prime. And then you have, or let's take this one, it's where the gamma is defined. So you've got your AZ here and your A prime up here. Then the cosine would be the adjacent, which is AZ over A. And that's going to be true for any of them. So the cosines of these direction angles are called the direction cosines. The cosines is nice because it's 0 to 180. That covers pretty much the whole spectrum if you have 3 of them. Now notice that if you sum these and square them, you're going to have AX squared plus AY squared plus AZ squared on top, A squared on bottom. And so that just gives you a 1. So they're not independent. If you give me 2 of them, I can find the third. And my unit vector, then I can either write as the cosine I hat, j hat, k hat, or I can go x over a because they're the same thing. So knowing the direction cosines lets you know the direction, and you can write your unit vector. So here's one where they give us a vector and 2 of the direction cosines. We can use the fact that the sum of the squares equal 1 to find the third. Now, because of the square root's ambiguous, we don't know whether to use plus or minus. Now, one will give you 60, one will get you 120, but when we look back and see it's in that first quadrant, then we know it's 60. And so we could write the unit vector as cosine alpha, cosine beta, cosine gamma, multiply that times the magnitude, and we have our vector in Cartesian form. There's the numbers, and we get out I, j hat, and k hat. Now take your calculator and show yourself that the sum of those squares, square rooted, will give you 200 magnitude. Another example is he gives me a little bit same information, almost, though it's not quite the direction cosines. The direction cosines are specifically from angle from vector directly to the axis. So this one's a little bit different. We'll just have to do a little bit more trig here. Notice we can get FZ because it's opposite. That is a right triangle. And so the Z part's going to be opposite to 60. So 100 sine 60. And then this part of it will be 100 cosine 60. And then that'll be the hypotenuse of these two, this dark blue triangle, with that being X and that being Y. And so I can take what I just have, and that's the hypotenuse. And so cosine 45 will give me the X, sine 45 will give me the Y. So he called it F prime. And there we have our X and Y parts. And since I have the parts, then I can then write it like that. I could then sum those and get the magnitude. Turned out it's 100. I can then go back and take f and divide it by the 100, and I will have my unit vector, a vector of length 1 that points in the same direction as our force. That's the direction cosine. So I could take the inverse cosine of each one of those, and that'll be the direction angle. So later in problems, he'll probably be giving us the direction cosines, and we'll use it to write our vectors. But for now, we want you to be able to sort of go both ways. So there should be some homework problems on that. If you have any questions, shoot me an email.